Hi, I'm Mark Barsamian with the Ohio University Math Department. In this video, I'll continue discussing Section 6.1. Remember that Section 6.1 is about neutral geometry. In the first video about Section 6.1, we discussed the definition of neutral geometry, that is, a protractor geometry that also satisfies the side-angle side axiom. And then we proved a couple of basic results of neutral geometry. That was facts that could be proven using just the side-angle side axiom and maybe some earlier facts from earlier chapters. In the current video, we'll start by discussing models of neutral geometry, and then we'll discuss some particular facts about the Euclidean plane, which is one of those models of neutral geometry. And then we'll see the introduction of an important theorem called the Isosceles Triangle Theorem, which I call the CS-CA theorem. And then we'll use the CSA theorem to prove some more sophisticated facts about neutral geometry. This material is from section 6.1, the side-angle side axiom, in the book Geometry: A Metric Approach with Models by Millman Parker. More specifically, this video corresponds to material on pages 128 to 129 of that section. The corresponding homework for this video is this collection of 7 exercises from section 6.1. This video is produced for Ohio University Math 3110-5110 College Geometry. Now there's quite a bit of stuff from previous sections of the book that'll be needed in this video. There's this theorem from chapter 4, theorem 4.4.6, that says, given a triangle in a Pasch geometry, remember that that is a metric geometry that satisfies the plane separation axiom. Given a triangle in a Pasch geometry, if P is a point between A and C, then P is in the interior of any triangle, ABC. So that's illustrated by this drawing. Here's an illustration of P being between points A and C. Here's an illustration of P being in the interior of triangle ABC. We'll use the definition of linear pair from section 5.3 to say two angles form a linear pair means that they can be labeled angle ABC and angle CBD, where B is between A and D. In other words, a configuration that would look like this in a drawing. And we'll need theorem 5.3.2, the linear pair theorem, that says in a protractor geometry, if angles ABC and CBD form a linear pair, then their measures add up to 180. Now notice in my illustration of this, I do not draw the conclusion in the following way. I don't do that because that makes it look like ABD is an angle, which it's not. Those are collinear points. They don't form an angle. And it also makes it look like that angle has measure 180, which it can't. In our geometry, angles cannot have measure 180. So I illustrate the conclusion of the linear pair theorem with this drawing, and I just have to have this equation as kind of a sidecar. We'll use the definition of angle bisector from section 5.3. A bisector of angle ABC is a ray BD with the property that D is in the interior of that angle ABC, and ray BD creates two angles with equal measure. Theorem 5.3.8 is also important. The theorem says if ABC is an angle in a protractor geometry, then that angle has a unique angle bisector. We'll use theorem 5.3.11, the congruent angle addition theorem. It says the following. In a protractor geometry, if point D is in the interior of angle ABC and S is in the interior of angle PQR, and angle ABD is congruent to angle PQS, that's the angles marked in green, and angle DBC is congruent to angle SQR, that's the angles marked in red over in this drawing on the left, then angle ABC is congruent to angle PQR, that's the angles marked in blue over here in the drawing of the conclusion. A very similar sounding theorem that we'll use is theorem 5.3.12, the congruent angle subtraction theorem. It has similar hypothesis, If point D is in the interior of angle ABC and point S is in the interior of angle PQR, and angle ABD is congruent to angle PQS, again marked in green as in the previous theorem, and angle ABC is congruent to angle PQR, that's these angles marked in red, then angle DBC is congruent to angle SQR, that's these angles marked in blue. Now, remember the fact that in our book, section 5.4, which we didn't cover, but we've discussed the fact that we are using the results. We've discussed that fact before. In that section, the sine and cosine functions are defined abstractly using calculus. Their definitions do not involve right triangles or the unit circle. And remember that the cosine function is a function that, as an abstract function, has domain, the set of numbers greater than or equal to 0 and less than 180, and has range, the set of numbers greater than or equal to -1 and less than or equal to 1. The sine function also has domain, that's the closed interval from 0 to 180, but its range is the closed interval from 0 to 1. And the sine function is defined by this equation. Sine theta is square root of 1 minus cos theta squared. The tangent function is not introduced in our book. It has domain the half-open interval, the numbers theta that are greater than or equal to 0 and less than 90. Its range is the half-open interval, that is, the numbers greater than or equal to 0. The tangent function is defined by this equation. Tangent theta is sine theta over cos theta. Now recall content from section 6.1 discussed in the previous video 6.1a. We saw the definition of triangle congruence. In order to formulate that definition, we had to have a notion of corresponding parts of triangles. So that notion, the definition of corresponding parts, is based on a function from the vertices of one triangle to another triangle, such that the function is a bijection from that set of vertices of one triangle to the set of vertices of the other triangle. If you have a function like that, a bijection of the set of vertices, then it automatically gives rise to a correspondence of 6 pairs of parts of the two triangles, as described in that list. And we saw this definition of congruence between triangles. These words, a congruence between triangle ABC and triangle DEF, mean this: a bijection, that is a function from the set of vertices of ABC to the set of vertices of triangle DEF, such that each of the pair of corresponding parts is congruent. That is, each of those pairs of corresponding parts that were listed in the previous green box is actually a pair of parts that's congruent. We defined congruent triangles to mean this. We say that two triangles are congruent to mean there exists a congruence. That is, there exists one of those bijective functions from the set of vertices of this triangle to the set of vertices of that triangle, such that each pair of corresponding parts is congruent. Now keep in mind that these words, triangle ABC and triangle DEF, are congruent. Those words do not have a corresponding symbol. We did see the definition of a symbol to indicate a particular congruence. Now this is confusing. The symbol is written this way, and it's often spoken triangle ABC is congruent to triangle DEF. Now that's confusing because I just said that those words don't have a symbol. But I just now said, here's a symbol that's spoken with those words. Well, it really shouldn't be this confusing, but it is. This symbol, spoken, triangle ABC is congruent to triangle DEF, should really be spoken more precisely. It means that triangle ABC is congruent to triangle DEF, but using this particular bijection of vertices. F of A equals D, F of B equals E, and F of C equals F. So this symbol is spoken the same way that these words are spoken, but this symbol actually means more than these words. It means these words are true and this particular bijection is the one that works. We discussed the fact that in a protractor geometry, congruence is an equivalence relation on the set of all triangles. And we discussed the side-angle-side axiom, the angle-side-angle axiom, the side-side-side axiom, and the angle-angle-side axiom. And finally, we saw the definition of neutral geometry. A neutral geometry, or absolute geometry, is a protractor geometry that also satisfies the side-angle-side axiom. And finally, we discussed the fact that just adding this single axiom to create the definition of neutral geometry gives us a whole bunch of other behavior that we can prove in theorems. We will prove this theorem. Every neutral geometry satisfies the angle-side-angle axiom. We'll prove this. Every neutral geometry satisfies the side-side-side axiom. And we'll eventually prove this. Every neutral geometry satisfies the angle-angle-side axiom. Now, we haven't proven those theorems yet, but it's just an introduction to material that's coming up. Okay, so that is a fairly long review of previous material. First topic for this new video is models of Euclidean geometry. So the question is, which of our familiar protractor geometries qualify to be called neutral geometries? Well, remember from video 6.1, example 3, that the taxicab plane does not satisfy the side-angle-side axiom. We considered this example of two triangles, this green triangle and this red triangle, that have corresponding side-angle-side that are congruent. And yet, the triangles are not congruent because the third side is not congruent. So therefore, the taxicab plane is not a neutral geometry. It does not satisfy the side-angle-side axiom. So even though it is a protractor geometry, it does not qualify to be called a neutral geometry. We could similarly show that the max plane is also not a neutral geometry. But it's shown in the book that our two most familiar models of protractor geometry do qualify to be called models of neutral geometry. In proposition 6.1.3, it's proven that the Euclidean plane satisfies the side-angle-side axiom, and therefore it's a neutral geometry. Now, that proof that's provided on page 128 uses the Euclidean Law of Cosines, which is presented just before that in proposition 6.1.2. It says this: if capital P, capital Q, and capital R are three non-collinear points in the Cartesian plane, then those three non-collinear points determine a triangle. If we label the lengths of the sides opposite those vertices with the small letters, so opposite vertex capital P is a side of length small p, opposite vertex capital Q is a side of length small q, and opposite vertex capital R is a side of length small r. So if we have those sides and vertices labeled that way, then an equation is true. Now there's a typo in the equation that I've written here. The equation should say that little q squared equals little p squared plus little r squared minus 2pr cos theta. So that's the law of cosines, the Euclidean law of cosines. Notice that these distances, little p, little q, and little r, are Euclidean distances. Well, that Euclidean law of cosines is used in proving proposition 6.1.3, that the Euclidean plane is a neutral geometry. And the book also proves this proposition that says that the Poincare plane satisfies the side-angle-side axiom and therefore is a neutral geometry. That's a substantially harder proof. It's not even presented in the book until much later. We won't study the proof in our course. The second topic for this video is some facts about the Euclidean plane. In your homework exercise 6.1, number 6, you'll use the Euclidean law of cosines to prove the Pythagorean theorem of Euclidean geometry. It says if triangle ABC, those are capital letters, has a right angle at capital C, this configuration, then if we label the sides opposite those vertices with small letters, then this equation is true. Little a squared plus little b squared equals little c squared. An important thing to note is that this is a theorem of Euclidean geometry. Remember, I mentioned that you'll use the Euclidean law of cosines to prove that. So it's the Pythagorean theorem of Euclidean geometry. Also in your homework, you'll use the Euclidean Law of Cosines and the Pythagorean theorem of Euclidean geometry to show that the trigonometric functions, this should say functions, defined in section 5.4 agree with what I call the Sohcahtoa definitions of sine and cosine that may have been your first introduction to those functions back in middle school. Notice that these results are valid only in the Euclidean plane. So remember, the Sohcahtoa interpretation of sine, cosine, and tangent says this: the sine of an angle is the opposite over the hypotenuse. The cosine of an angle is adjacent over the hypotenuse, and the tangent of an angle is opposite over adjacent. Notice that those definitions of sine, cosine, and tangent refer to a triangle. They refer to right angles. They refer to angles. Our abstract definition of sine, cosine, and tangent from section 5.4, those abstract definitions were formulated in terms of calculus. So they did not use any reference to triangles, to right angles, to angles. So this is an important corollary, that your old ideas of sine, cosine, and tangent agree with the abstract calculus idea of sine, cosine, and tangent. The third topic for this video is the CS arrow CA theorem. Now, in preparation for discussing that theorem, I'll need to discuss different types of triangles in a protractor geometry. Given a triangle in a protractor geometry, the triangle is called scalene if no two sides are congruent. In other words, all three sides have different lengths. A triangle is called isosceles if at least two sides are congruent. In this middle triangle, these two sides are congruent. In this triangle on the right, all three sides are congruent. A triangle is called equilateral if all three sides are congruent. So this triangle on the right is both isosceles and equilateral. This triangle is isosceles but not equilateral. Theorem 6.1.5, the Isosceles Triangle Theorem, also called Pons Asinorum in the book, I prefer to call this CS arrow CA, says this: in a neutral geometry, if two sides of a triangle are congruent, that's this picture, then the angles opposite those sides are congruent. That's this picture. So in my naming of the theorem, the CS is the hypothesis, that is, two sides of a triangle are congruent, and the CA is the conclusion, the angles opposite those sides are congruent. Notice the naming convention. The theorem is called the Isosceles Triangle Theorem. That name refers to the situation described in the hypothesis. Two sides of a triangle are congruent. That is, if you have an isosceles triangle, then the angles opposite the sides are also congruent. So notice that the isosceles triangle theorem cannot be used to prove that a triangle is isosceles. The isosceles triangle theorem is something that you use in a situation where you already know that a triangle is isosceles. It tells you that in that situation, the angles opposite those sides are congruent. Those angles are referred to sometimes as base angles. So this theorem says, if a triangle is isosceles, then its base angles are congruent. So let's prove this theorem. We start by supposing that a triangle ABC has side BA congruent to side BC, so as drawn in this picture. Then we introduce a bijection between the vertices of triangle ABC and triangle CBA. The bijection is this: vertices ABC correspond to vertices CBA. So we imagine basically two copies of the same triangle. One copy is drawn this way, the other copy is drawn this way, but it's the same triangle. Using this correspondence of vertices, we get these corresponding pairs of parts. Side BA of the left triangle corresponds to side BC of the other triangle. And angle ABC of the triangle on the left corresponds to angle CBA of the triangle on the right. And then lastly, side BC of the triangle on the left corresponds to side BA of the triangle on the right. Now observe that the corresponding parts in each of these three pairs are congruent. That is, we have parts of triangle ABC congruent to parts of triangle CBA. We were given that BA is congruent to BC. We know that angle ABC is congruent to CBA because it's congruent to itself because it has the same measure as itself. And we know that side BC is congruent to side BA. Therefore, we can say that triangle ABC is congruent to triangle CBA using this symbol that indicates that those things are congruent using that particular correspondence. Now notice the way that I draw this. I draw the triangles side by side, and I shade their interiors to indicate the triangles that I'm referring to, and I put a congruence symbol inside of each of them. So I'm indicating that those triangles are congruent. But also in these drawings, I show the parts that are mentioned in the justification. The side angle side congruence axiom uses the fact that the side angle side of this triangle is congruent to the side angle side of that triangle. Now therefore, we can say that angle BAC is congruent to angle BCA by the definition of triangle congruence. Remember that two triangles are defined to be congruent if all of their corresponding parts are congruent. Well, that was our goal. Our goal was to prove that angle BAC is congruent to angle BCA. Notice it's written abstractly in words here without pictures. Throughout this proof, all the pictures were nice to help us understand what was going on, but they weren't necessary for the integrity of the proof. All the words comprise the proof. I'm saying that because it might look weird that I drew this as our conclusion, when the conclusion that we drew in the statement of the theorem looked like this. We are talking about two angles that were parts of a single triangle. But I find it, for me, just clearer to keep referring to these triangles as if they were different triangles. They're not, but just keep referring to them as different triangles, and then refer to their congruent parts. Let's go on. The fourth topic for this video is using the CS arrow CA theorem, that is the Isosceles Triangle Theorem, to prove a fact about special rays in triangles. First of all, what do I mean by special rays in triangles? Well, given a triangle ABC in a protracted geometry, there exist three special rays from vertex A. The blue ray in this picture is a ray from A that is perpendicular to side BC. The red ray in this picture is a ray from A that bisects angle BAC. Notice that this angle is congruent to that angle. The green ray in this picture is a ray that bisects side BC. Notice the green ray goes through this point M that's a midpoint of side BC. So it's important to realize that these three rays are not, in general, the same ray. In this picture, you can see that they're not. The blue ray, the red ray, the green ray are different rays. But it can be shown that in neutral geometry, if triangle ABC is an isosceles triangle with AB congruent to AC, then the three rays are actually the same ray. Parts of this fact are proven in various places in our book and in my videos. In example 1, we'll prove that if triangle ABC is an isosceles triangle with AB congruent to AC, and if M is the midpoint of side BC, then that green ray, AM, the ray from A that bisects side BC, is the same as that red ray, the ray from point A that bisects angle BAC. In your homework exercise 6.1 number 8, you'll prove that in neutral geometry, if triangle ABC is an isosceles triangle with AB congruent to AC, and if M is the midpoint of side BC, then ray AM, that is that green ray from point A that bisects side BC, is also the blue ray, that is the ray from A that's perpendicular to BC. So let's do example 1. In neutral geometry, if ABC is isosceles with side AB congruent to AC, and if M is the midpoint of side BC, so there's the hypothesis configuration, then ray AM bisects angle BAC. So again, that green special ray is the same as that red special ray in the particular situation that you have an isosceles triangle. So how do we prove this? Well, suppose we have the given configuration of points. Triangle ABC is isosceles, and M is the midpoint of side BC. The first thing we can do is use the CS arrow CA theorem to say that these base angles are congruent. So remember that in this part of the video, we're going to be using the CS arrow CA theorem to prove other stuff. So here we are using the CS arrow CA theorem to say that those base angles are congruent. Once we've got those base angles congruent, we can say that that left triangle, that triangle that's shaded, whose interior is shaded green, is congruent to the triangle on the right, whose interior is shaded red. Now the justification for that is the side angle side axiom. So there you see my illustration. I've shaded the interiors of the triangles and I've put the congruence symbol. But I've also included the objects that are mentioned, that is, the objects that are implicated in using the side angle side axiom. The side angle and side of the green triangle that are congruent to the side angle side of the triangle on the right. In statement 4, we can say, therefore, that these two angles are congruent. This angle of that triangle on the left is congruent to this angle of the triangle on the right. Now you might think that we're done. It looks like we have an illustration of ray AM being a bisector of angle A. But remember, the definition of bisector says more than just that it creates two congruent angles. Notice what comes next. We have to prove that point M is in the interior of angle ABC. That's by one of those old theorems that I mentioned in the review at the beginning of the video. Since point M is known to be on the side BC and is not one of the endpoints, that is, it's in the interior of side BC, we can say, therefore, that point M is in the interior of that angle. So finally now, we can say that this ray AM bisects angle BAC. That's using the fact that it creates congruent angles from step 4, and the fact that point M is in the interior of that angle from step 5. And that's the end of that proof. Let's go on. The fifth and final topic of this video is to use the CS arrow CA theorem again to prove a more sophisticated congruence. So this example is similar to your homework exercise 6.2 number 10. It says the following: in neutral geometry, if a triangle ABC and points D and E satisfy all these conditions, D is between A and B, and E is between A and C, and AD is congruent to AE, marked in red, and angle BDC is congruent to angle CEB, marked in green, and segment DC is congruent to segment BE, marked in blue. It's hard to mark congruent segments when they cross. Color is useful for this kind of situation. If all of that stuff is satisfied, then angle BCD is congruent to angle CBE, marked in red here. Well, here we go. Here's the proof. Step 1, we suppose all the given stuff, so this configuration of objects with those congruences marked. The first thing that we do is we prove that angle ADC is congruent to angle AEB. Now I've got that marked in blue here. Now why is that? Well, it's because, first of all, we can apply the linear pair theorem to these two angles to say that angle ADC, that blue angle, is 180 minus angle BDC, that green angle. And then we use the fact that angle BDC is given as congruent to angle CEB. So these two green angles have the same measure. And then finally we apply the linear pair theorem to this pair of angles. That pair of angles is a linear pair, and so this quantity is equal to this quantity. And that proves that the measure of angle ADC is equal to the measure of angle AEB. Then we can prove that triangle ADC is congruent to triangle AEB. That's by the side angle side axiom. Now we have to say how we're going to apply it. We apply it to this configuration of side, angle, and side being congruent. And notice the drawing that I've made. We had before a drawing of all these parts as part of a single triangle. Parts are overlapping, it's kind of crowded. Here I've extracted the two triangles that I'm talking about, and I've drawn them side by side, not overlapping. Notice also in the drawing I've done my usual thing. I've shaded the interiors of those triangles and put a congruent symbol indicating that I mean for the reader to interpret them as being congruent. Also, I've included all the objects that are implicated in using the side angle side axiom. All of these objects are marked in these drawings. The next thing we can do is use the fact that the triangles are congruent to say that this particular pair of sides is congruent. And again, I'm keeping those triangles separate in order to make these statements clearer in their illustrations. Can also use the definition of triangle congruence to say that this pair of angles is congruent. Those are corresponding angles, and they're in triangles that have been proven to be congruent, so those angles are congruent. And then finally we can say that this pair of angles is congruent. Now that's by the CS arrow CA theorem, and it's applied to triangle ABC with known sides AB and AC being congruent. Now notice again, I draw an illustration showing only the objects mentioned, and notice that when you use the CS arrow CA theorem, you have to mention what triangle you're applying it to and what sides you know are congruent. Well, here on the left I have a drawing of the triangle that I'm applying the theorem to, and it's got marked the sides that are known to be congruent. The drawing of the conclusion shows the base angles that we know are therefore congruent. So again, I can't stress enough that when you use the CS arrow CA theorem, you need to mention precisely what triangle you're applying it to and what two sides are known to be congruent. And you should have a drawing that shows that triangle. Notice this drawing does not show two triangles. The hypothesis of this theorem is you have an isosceles triangle with two congruent sides. The conclusion of this illustration does not have two triangles. It has a single triangle with two base angles that are congruent. Now, let's keep going. The next thing we prove is that point D is in the interior of angle ACB. That's this illustration. We prove that by using that theorem 4.4.6 again. We know that point D is on the interior of a side of that triangle. We draw the triangle and that side highlighted, point D highlighted, and we use this theorem to tell us that therefore D is in the interior of that angle. And we can say that point E is in the interior of that angle, using again that theorem 4.4.6. So finally, we can prove the thing that we are trying to prove, that this angle BCD is congruent to angle CEB. That's marked in red. How do we prove that? Well, we use that congruent angle subtraction theorem applied to this configuration of points. We have point D known to be in the interior of angle ACB. We have a point E that's known to be in the interior of angle ABC. And we know that these green angles are congruent. And we know that these blue angles are congruent. So when we apply the theorem, it tells us that therefore these red angles are congruent. And that was the goal of our proof. Our goal was to prove that these angles are congruent. In the illustration of the statement of the claim, I have these angles highlighted in the configuration of points and segments that are given. That is, this drawing was described in the hypothesis, and I highlight these angles in the same drawing. But when we got around to proving that those angles are congruent, it was in a drawing that looks like this. Now, I suppose it might be helpful if I would put that back into the original drawing. That is, maybe bring this drawing down for the final conclusion, but I didn't, but maybe that would be helpful. Well, that's the end of that proof, and that's the end of the video. Thank you.